Nous avons vu dans ce qui précède.
We have seen in the previous lesson the principal radiation processes in astrophysics. Radiation can be collected by telescopes or by antennas, depending on the wavelength range. Observatories can be placed on the ground if the atmosphere doesn't interact too much with the radiation from stellar objects or in space. For every case, we need to be able to quantify. We have to measure the radiation. We will see in the following how astronomers measure the luminous flux, the color of stellar objects, and how to estimate the luminous power of stellar objects. How can one analyze light? Either on analysis light through the spectrum, so the luminous intensity in function of the wavelength, or one integrates light through filters, where we filter only certain wavelengths, thanks to filters, which have here a transmission curve. The high end of the curve is where we let pass the most light at a certain wavelength, and the low sections of the curve is where less light goes through. So these filters are actually optical filters, which we put behind a telescope. So here we have a blue filter, for example, which lets only pass blue light and blocks out any other wavelength. So we can have lots of series of filters. Here is a red filter, and here another one, even redder, and here another one, redder still. So light will be filtered. Here we have 4 optical filters which we can give names to. For example, this one is the B filter for blue, V for green or visual, R for the red filter, and here I for infrared. The eye starts not being able to see at the wavelengths beyond these or below these. Cameras can, however, see very well at these wavelengths. So the goal of a filter is to select ranges of wavelengths. Once the wavelength ranges are selected, one can integrate the light in the filters and see the spatial distribution of the light, and that is, of course, an image. So here we have the B filter. We will integrate the light here in a certain filter. So we multiply the spectrum by the transmission curve and integrate it over all wavelengths. This will give us the flux in a certain bandwidth. And the flux in the bandwidth, in function of the spatial position, is an image. An image is the luminous intensity of a certain wavelength and at a certain pixel. So we can take images at all wavelengths. Here we have the image corresponding to the blue filter for the 5555 angstar MS filter of the Hubble Space Telescope. We can do, of course, the same thing at different wavelengths. So we integrate the flux in one wavelength range and note the value of the minor flux in function of the position. So we get here, for example, an infrared image at a wavelength of 8140 angstrom ms. So here we have a galaxy as seen by the Hubble Space Telescope at a red wavelength, here almost infrared, and at the blue wavelength, here almost ultraviolet. What can we see in these images? On the left here, we see an image taken with the Hubble Space Telescope of a galaxy, and here the same galaxy with the same field of view, taken with the infrared filter. What we see is obviously different, since objects have different spectras. Some objects will appear more clearly on the blue filter, and others will appear more clearly on the red filter. So we see some objects of this type. If we look here, for example, we see a star that has a weak luminous flux in the optical wavelengths, but a strong one in the infrared. We know already here that the star is a red star. Now there are star formation zones in galaxies. Stars, we have seen in the lesson about black body radiation, when they are young, hot, and massive, radiate more in blue. That is why we see here star formation zones, which appear strongly in blue filters. But the contrast with other regions is less distinct in the red filter. So we have here a zone where stars are young, hot, massive, and blue, and so radiate more in the blue than in the red. We can have certain dust stones, for example. We have here one in the spiral arms of the galaxy. Dust absorbs strongly blue light, much less than red light. So we have a contrast here, which is very strong between dust stones and the rest of the galaxy in blue, while the contrast is much weaker here in the blue. That is simply because red light passes through dust more easily than blue light. A way of visualizing this is to make an image in true colors. It is more a false color images, but where the colors are coded, so that the eye finds the color map, which it is used to. To take an image in true colors, we take a spectrum, or in other words, we take an image. We have, for example, a spectrum. We will symbolize a spectrum like this. And then we take the filter, for example, the blue one from the Space Telescope. We will integrate the light over a certain range of wavelengths. We will take the red filter we had before. We will integrate the light here, where we have the blue filter. The red filter, and in this case we even added the optical H-alpha filter, which you will remember is the one with the most important lines of the hydrogen atom. This line is at 6,563 angstrom ms. If we visualized it on this spectrum, it would be something rather narrow like this. This line is typical of star formation, and therefore it is interesting, which is what has been done here, to add a narrow filter, which is the H-alpha filter, which will catch just a narrow hydrogen line. So now we will make an RGB image. So red, green, visual, and blue. The blue part of the image, the blue pixels, will be coded with the image that was taken, with the blue filter, the B filter. For the green part of the image, the red optical image will be used, and then we will take the H-alpha line for the red part. Each time a pixel has a high flux in this image, it will appear red. When it has a high flux in this image, it will appear blue. And if it has a high flux in this image, it will appear green. Now we can combine all this into one image. We take a weighting of the same pixel in the three images, and then make a color image. In this color image, we can see, for example, the star we never saw before, which was very red, or at least the point that was in the image, and that was very red. We see the blue star formation zones. There are lots of small blue points that are massive stars in formation, almost formed, but which emit very blue radiation, so very hot black bodies. And then we find a certain number of red zones, here for example. So that is the H-alpha radiation. The pixel with high flux in this image here, H-alpha, appear in red in the image. When you see this image in false colors, they are not just there to be pretty. We can easily see here the physical processes that can cause different types of radiation. So in blue, young, hot and massive stars. In red, gas zones ionized by massive stars. Each time we have massive stars, we see them directly in blue. But we see them also by the ionization they cause in the hydrogen clouds. There we see the hydrogen, H-alpha line, which is produced by the excitation of the hydrogen atoms, which de-energize themselves by emitting the famous H-alpha line. So astronomers like using logarithmic scales to quantify the luminous fluxes and the luminosities. We have already seen the luminosity, for example, of a star at a certain wavelength, let's say L, lambda. And this star is situated at a certain distance from us. We will capture the radiation at a certain distance, d. And this radiation will be diluted, if it is isotropic, over a sphere with a surface of 4 pi d. So here, we will have the flux F lambda. And this F lambda flux will be equal to, as we have seen before, L lambda. So the luminosity divided by 4 pi times the square of the distance. Now, to take into account what the ancients saw, and with the logarithmic scale of the eye, the astronomers have decided to measure the luminex flux, not in flux, but in magnitude over a logarithmic scale. This logarithmic scale is defined as minus 2.5 log flux at a certain wavelength, lambda in this case. Now we can also integrate the flux through a filter. So we can define, for example, if X is a filter for a certain bandwidth. For example, B, V, R, O, U, I, as we defined earlier. So X can be one of those letters. The magnitude of the X filter will be minus 2.5 log base 10 of the integral f lambda d lambda. In other words, we will have mx equals minus 2.5 log of the total flux in X band. This flux is a flux expressed in ERG by seconds, so a power by cm. So we have no angstar ms anymore, because we integrated over all wavelengths. We have a power by cm, which is a power flux. So now, how do we calibrate our flux scale? In fact, the calibration will be the Vega star, an extremely bright star in the northern hemisphere. So we define the magnitude as being equal to 0 in the V filter. Let's see how this works. We take an object, of which we want to measure the magnitude, and the Vega stars, so alpha in the Lyra constellation, and we will integrate the flux of the object in the V band. Here we have the transmission of the V band. We will do the same with the Vega star. Here we have a certain flux in the V band of our object. And here we have the flux in the V band of the Vega star. Of course, we can do that with any other band. So the flux in the V band will be, by definition, the integral of the f lambda times the transmission of the Vd lambda filter. And then, to simplify, we normalize and say that the transmission integral of the filter is equal to 1. In other words, we erase that term from the equation above. Now the flux will be rescaled in function of Vega, which means that the magnitude of the V filter of our object will be minus 2.5 log of the flux in the V band of the object, rescaled to the flux in the V band of the Vega star. So this flux divided by this flux, we take the log minus 2.5 and we have the magnitude of our object. There is something here we don't see, because in fact, we said that this is also equal to the magnitude in the V band of the object, minus the magnitude in the V band of Vega. And this is equal to, now by definition, the Vega magnitude in the V band is equal to 0. So the magnitude of the object is the same as this one. Therefore, the magnitude of an object equals minus 2.5 log of the flux, and it is always rescaled to Vega. So we know by how much something is more luminous or less luminous than Vega on a logarithmic scale in a certain band, here the V band. And there is this minus 2.5 factor that transforms the object or quantitative scale to a more subjective scale, that is the logarithmic scale of the human eye, which is, of course, the scale used by the ancients to characterize the brightness of the stars. So we have measured the flux of objects in different boundaries in function of the flux of Vega in different boundaries. Now we will measure the flux ratio of the same object, but this time with different boundary. For example, here, we will have the measured flux ratio for an object in the V band. So Fv of the object, and we will compare this to the flux of the same object in the I band. In other words, what we measure here is the slope of the spectrum between the two bands. And this slope has to be calibrated, so we will measure it in function of the same flux ratio between two bands for the Vega star. I will measure the slope of my spectrum in function of the slope of the spectrum of the Vega star. So here I will define notations. We have Fv of Vega, and here Fi of Vega. And now, if we express all this in magnitudes, the magnitude of my object in the V band minus the magnitude of the object in the I band, we find the following equation from what we have seen in the earlier slides. This is simply the magnitude difference of my object in function of Vega between the V band and the I band. Now we can rearrange a bit the equation. I can write mv minus mi. Here, after rearranging the equation, what we measure here is the flux ratio of our object in the V band in function of the I band. We compare this to the Vega flux ratio in the V band in function of the I band. In other words, we look at the relative slope of my object in function of the relative slope of the Vega spectrum. So we will look at the color of the object compared to that of Vega. So in practice, we will use different color indexes. So instead of writing M indexed V and I, often we will write in big letters like this. For example, V minus I, B minus V. And we will define color indexes. And in these color indexes, we will always put the bluest filter left. With these conventions, a big color index will be typically a red object, and a weak color index will be a blue object. For example, B minus V big is typically a red object, so redder than Vega, and B minus V small will be a blue one, so bluer than Vega, since everything is scaled to the Vega star. So we have defined the fluxes, the luminosities, the magnitudes, and the color of the stars and stellar objects in general. We will now define another extremely important quantity in astrophysics, the absolute magnitudes. In fact, the magnitude of an object seen at a distance of 10 parsecs. So we will say that absolute magnitudes are in fact visual magnitudes, the small m we saw earlier, seen from a distance of 10 parsecs. That is the magnitude of an object if it is seen from 10 parsecs. So of course, the visual magnitude, which is minus 2.5 log of the flux, where the flux is again what we defined before L. That is the luminosity of an object, diluted over a certain surface here, where we have a certain flux. And the flux is equal to 4 pi d. So the absolute magnitude will minus 2.5 log of flux when d is equal to 10 parsecs. We can calculate the difference between the two magnitudes, the visual magnitude rescaled to Vega and the magnitude at 10 parsecs. So again, we use the definition of magnitudes, minus 2.5 log. So the flux is L divided by 4 pi d. And the absolute magnitude, as we said, is the flux of the object if it is seen from 10 parsecs away. So we use here already the right units, 4 pi times 10 squared. Now, we see that this is equal to minus 2.5, 1 of 10 squared over d squared. In other words, m minus m is equal to 5 log d minus 5. And that is an absolutely fundamental equation in astrophysics. A key result, since it is this equation which allows us to measure distance, thanks to, for example, standard candles, supernovas, or Cepheid stars, which we will see later. This is called the distance module with d in parsecs. By definition, the difference between apparent magnitude and absolute magnitude is plus 5 log d in parsecs minus 5. So we can immediately see that if we can get an object for which we measure the apparent magnitude and for which we know, in an independent manner, the absolute magnitude, we will be able to know its distance. The measurement of the distance is one of the tasks that are extremely important in astrophysics. Measuring the distances and the mass are two key components for the understanding of the formation and evolution of stellar objects. Now, some orders of magnitudes of well-known objects. So here we have the apparent magnitude for a series of objects. And here we have the absolute magnitude of different objects. So this is the absolute magnitude. This is, of course, the apparent magnitude that an object would have if it was placed at a distance of 10 parsecs. So the sun has the smallest magnitude of all objects in the sky. So it's the brightest object, in appearance at least. Because if we put it at 10 parsecs, its magnitude is plus 4.8. Plus 4.8 is around the magnitude that's almost invisible to the naked eye objects have. So the sun, at a distance of 10 parsecs, would be a weak star indistinguishable from the rest, in fact, almost invisible to the naked eye. So now, at the complete opposite of the scale, we take an extremely weak object with a high positive magnitude. So for example, some very distant quasars. These objects are almost invisible with the biggest actual telescopes. And if we put these objects at a distance of 10 parsecs, they have a magnitude of -30, so they would be, if they were at 10 parsecs from us, a lot brighter, 3 magnitudes brighter than the Sun. So we can see through this comparison of apparent magnitudes and absolute magnitude to which degree the distance of the stars dominates what we perceive from their radiation. The challenge in astrophysics is to imagine, to modelize the physical processes that account for the received radiation. This radiation can be captured in the form of an image or a spectrum. It is these, and only these, that will permit us to understand the functioning of the stars that compose the universe.